This is a video tutorial on how to use the chain rule to differentiate certain equations. My previous video, I used the chain rule to differentiate equations, but that was not using trigonometric functions. But this video specifically, a part one of two, where we're going to be using trigonometric functions and using the chain rule to differentiate them. The first video is going to be more straightforward functions, and then the next video is going to be where the arguments of these trigonometric functions are a little bit more complex. It just adds an additional step. So the first thing to note is the top line here. I've denoted an f of gx. So the chain rule is used on composite functions, which basically means you have one function inside of another function. So here labeled in blue you have g of x. So that's just an individual function. But you can see that there's a wrapper. It's wrapped in a function f. So the function f is the outer function and the function g of x is the inner function. So using that fact, we have to use a specific differentiation method in order to differentiate functions that are of this form, and that is the chain rule. So the chain rule here, I'll break this equation down into individual parts. So this is just what we had above. This is just a composite function where g of x is the inner function and f g of x is the f is the outer function. So then this d dx, which I'm sure you're familiar with, is just the differentiation operator that denotes that we're going to be differentiating this composite function with respect to x. So that is equal to the outer function differentiated. So you can see the little prime here that denotes the f function differentiated, and you can see that the inner function g of x stays the same. There's no operator on that at the moment, so that stays the same. Now that is in product with g of x that is being differentiated with respect to x. So just once more, using the chain rule to differentiate an f of g of x, first we differentiate the outer function, leaving the inner function as it is, and that is in product with the inner function differentiated. So once you put them parts together, that's you complete. You've used the chain rule to differentiate the function. Now that we know what the chain rule actually is, I'm just going to go through the top right hand side. You can see essentially they're just differentiation on the trigonometric functions that you just need to learn off. So there's obviously going to be derivations of how they come about, but for the purposes of answering questions and doing assignments and whatnot, you can just learn them off unless it specifically asks for a proof. So the first one, when you differentiate sine of x, you get cosine of x. When you differentiate cosine of x, you get minus sine of x. When you differentiate tan of x, you get a sec squared x. And then when you differentiate an e of x, an exponential, that is equal to e of x, which is quite interesting, purely because we know that differentiating is just getting the slope of the tangent with respect to the function. And when you differentiate, so we know the exponential goes from near zero and it increases at an exponential rate up like this. And if you take the slope at any tangent point on that line, it's just going to be 1. So that's why differentiation of e of x equals e of x. Alright, so chain rule, the terms that we just need to learn off, and now we can go straight into the examples. Alright, so the first one, I'll explain the first one and then we'll kind of rattle through the other ones, and yeah, we can see how we get on. So y is just our function with respect to x, and we have a 2 sine of x. So the important bit to note here is, alright, we need to use a chain rule. So what's the outer function, what's the inner function? Because once we know them, applying this is very straightforward. Well, we can see that sine is the function here, it's the outer function, and our inner function is its argument here, which is just x. So this 2 is just a coefficient that doesn't really come into it at the moment. So the sine is going to be the f and the x is going to be the g. Outer function, inner function. Alright, so now we've noted that the sine, just put down here, so that's the outer function and then x is the inner function. Right, so now we just want to apply the chain rule, so dy dx, so differentiating the function y with respect to x. So we know that 2 is just a coefficient, so that 2 can just stay as it is. Now sine, the first bit of the chain rule, we go to this component here. So we can see what we encounter first is this outer function differentiated. So then we have to differentiate sine as it's our outer function. And how do we know what the differentiated version of sine is? Well, we just learned up here that it's cosine of x. So then you might think, okay, well, that's fine, but what happens to this x in here? Well, this can actually stay the same. You'll see in the next video why, but if you differentiate this inner function x to the 1, you're just going to get 1. So when you put that in product with it, it's just going to give it be itself. So for the purposes of these examples, the argument is just x, so we can just take it that sine of x differentiated as cosine of x. All right, so sine of x differentiated as cosine of x, so that's going to be 2 cosine, or cos of x. And that's it done. Right, so the reason why we know this is done is because, yes, you can learn them off, but it kind of helps to understand where the chain rule came into it. So we differentiate the f part, which gave us the cosine, and the g of x is our inner function, and that stays the same, you can see. And then that's in product with the inner function differentiated, which would be the inner function is the x. That differentiated is just 1. So when you bring that in front, it's just going to be 2 cosine of x. That's why we can jump straight to these. Okay, on to the next one. So we'll go through the others a little bit quicker now. So it'd be good if you kind of stop the video and just maybe try one or two and then continue on to see if you're on the right path. Right, inner function and outer function. So our inner function, this is just, it might look a little bit more complicated than it needs to be, but that's essentially the same as a half multiplied by sine x. So it's essentially the same. You have a coefficient and you have sine of x. So we can see our sine is our f, which is our outer function, and x is our g of x. So again, this is what's happening using the chain rule by differentiating the outer, leaving the inner, then multiplying it by the inner function differentiated. But for the purposes of these examples, we can just take it that, okay, we have a half here, and then sine of x differentiated is cosine of x. Right, so that that's equal, just for completeness, that's cosine over 2, just to make it look a bit more of this form. Right, next one. So we want to differentiate this whole y function with respect to x. Well, the first one is we've seen before. We're just going to use the power rule. So that x is just the same as x to the 1. So we know that we differentiate this by bringing down the coefficient. So that's going to be 1 by x, which just gives us x. And we reduce the power by 1, which gives us 0. So that will just be 1, because x to the 0, or anything to the 0 is just 1. All right, and then there's a addition sign here, and then we're differentiating cosine of x. And up here we can see that cosine of x is minus sine of x, which then just, bringing out the minus, is just 1 minus sine of x. All right, so just we differentiate the first expression and then we differentiate the second expression. So they were two different. The first one we can just use the power rule. The second one we use the chain rule, but knowing the cosine x equals minus sine x, we just applied that straight off. All right, so d, our y function, is 3e to the x. So we want to differentiate that with respect to x. Well, this is quite straightforward. So we have our coefficient of 3, which just sits outside, and then we're differentiating the function, which is e to the x. Now we can see up here, because of what I explained at the start, that the slope at any point on an exponential is just 1. So it's just going to be 1 times e to the x. And that's why d dx e to the x is equal just e to the x. So if we're differentiating e to the x, we just get e to the x. And that's it done. Again, the next video will have more complicated powers here, and then that'll be, what you'll do then is you'll actually use the chain rule to the full extent. Technically we are still using it, but we're not going through inner and outer functions. We're just taking these as fact, where, okay, we see an e of x, that differentiated is e of x. Implicitly, we're using the chain rule each time. All right, our next example is y x squared plus e to the x. Well, x squared is just going to be our power rule that we're familiar with. So we're going to bring the 2 down to be a coefficient. And then we're going to have our x and our power reduces by 1. So 2 minus 1 is just 1, which is the same as just 2x. Next expression is e to the x. We differentiate e to the x, we get e to the x. Okay, our next one has one trigonometric function and then this exponential here. So again, dy dx, so sine differentiated, we know was cosine of x, cos of x, and we have a minus, and we have a e to the x differentiated is e to the x. And then our final example is 3 tan x over 4. Sometimes a fraction just makes it more complicated than it needs to be. So rewriting, it might look a little bit simpler if we just take out the 3/4 and then we just have tan to the x. So that just makes it a little bit easier to look at. So then if we differentiate this, the coefficient just stays where it is. And then tan x differentiated, we know is sec squared x. So that's just going to be sec squared x. And if you just wanted to put it in the same form as the original question, that would just be 3 sec squared x over 4. So I hope you enjoyed it. I hope it made sense. And a like and subscription would be great. Much appreciated. And yeah, see you in the next video. Thanks.